Hello, everyone. Today we're going to talk about permeability techniques, which are utilized for measuring water vapor transmission rate or gas transmission rate from various polymers. So before we go through the techniques that are utilized, what we need to understand is we need to understand the concept of permeability versus transmission. So not only that, there are various terminologies and the idea of mass transfer or permeability. So we need to understand the basic underlying concept, and then we will follow up with the various instrumental techniques which are utilized to measure the transmission rate. And there is a difference between the transmission rate and permeability coefficient. We will understand those differences. And finally, we will learn how to convert transmission rate to permeability coefficient. In addition, we will also learn about how to work with the multi-layer materials. How do we convert? And there are mathematical equations like Arrhenius equation. For example, if you are aware of transmission rate at a particular temperature and you are aware of a permeability coefficient at a particular temperature, how do you mathematically figure out the permeability coefficient at another temperature? So when we talk about packaging and permeability, so the basic idea or the basic understanding would be that an ideal package is a package which is a perfect barrier between the product and the environment. So, if there is no chemical changes happening in the product, there is no interaction between the package and the product, that would be perfect, right? So to have that, we need inert material. So inert is chemically non-reactive. There is no chemical interaction happening. So that kind of concept is more valid and more relevant, particularly when we are talking about processed food, right? So now consider certain scenarios here. You have so here is the question: is high barrier always desirable? So there could be scenarios where a complete barrier and no transmission may not be the ideal choice. You have example of couple of fresh produces right here. For example, you have strawberry here, you have potatoes here. When you see the clamshells of some of these produces, right? So what's going on is this fresh produce is live. That means it's breathing. So these produces, they consume oxygen. After harvesting, they consume oxygen from the environment and they release the carbon dioxide. So to survive, these produces, they need to breathe oxygen. If we completely seal a package like you see right here, initially you would have oxygen present inside the package in the headspace. And what would be the composition of the gas in the headspace? So when you package, the package environment that you're using would be the composition of the gas inside. So if you're packaging with the air, you have 20% oxygen or 20.8% oxygen. That oxygen concentration inside the package in a very good sealed package will drop very, very quickly. Within a day or so, you would see it will drop from almost 20% plus to like 3 to 1%. And if it gets that low and your carbon dioxide will increase, if the oxygen gets that low, your product will start rotting after day 2 or day 3 inside a completely closed package. So that's why when you see those clamshell packages in the market, they have holes. The holes are designed so there is an air exchange happening between outside and the inside. You have another example of a potato bag right at the bottom, and you may have noticed there are various holes inside the bag. The same idea applies here. So this example, these examples of the producers, they are indicating that a completely good barrier, no exchange of gases, may not be a good strategy, may not be a good idea for various products. You see, there are a couple more. There are a couple more packages right here. You have the example of crackers or cereals. Now, the crackers or cereals, they are packaged inside a polyolefin kind of bag right here. Now, the cereals or cracker, they are hygroscopic or hydrophobic in nature. That means they will quickly bind any water that will be present inside the package. So what happens is we need to protect these crackers or cereals from the humidity. So the humidity that's present outside in the atmosphere, that can migrate into the package. So in other words, if we gain water molecules which are undesirable in this case, they can lead to the end of the shelf life. So now the concept of shelf life, now I want to clarify one thing here. When we say shelf life, now the food may or may not be really bad to consume. It could be simply because the taste, the aroma, the flavor is not present, so consumer is not accepting. So consumer can reject the product just because the flavor and taste is not desirable in various cases as well. And naturally, in other cases, you can have chemical changes happening in the product that will also lead to end of the shelf life. So the example that you have here, the transmission is happening from outside to inside. Now you see the third example here, you have soda bottles. Now the soda bottles, they are pressurized and they have carbon dioxide trapped inside the bottle. And in this case, if we lose carbon dioxide, if we lose the carbonation, the customer is not going to accept this product. And you have another example of bread. Now, some of the breads, they have higher water content or higher water activity. And if we lose the water from the bread, it's not desirable. So that's why in some of those breads, you would see multiple layers of packages, 2 layers of films to contain the moisture. So in this case, in both of these examples, soda and the bread that you see, the loss of desirable molecules, which is CO2 and water in different products here. So that will lead to the end of the shelf life. So the point I'm making is in some of these cases, high barrier may not be desirable. In the other cases, your transmission may occur from inside to outside, which is, for example, in the soda. And in other cases, you have transmission happening from outside to inside. So what is directing, what is leading that molecules can move either into or out of the package. What is the force which is behind the movement of the molecules? The pressure difference of the gaseous molecules or water vapors, that is primarily the driving force. So the molecules will always move from higher air pressure or higher water vapor pressure to the lower air pressure. So that's how the wind also flows. So molecules will always move from higher pressure side to the lower pressure side. So these are some of the takeaways from the slide here. Now, the concept of barrier is also linked with product package interaction, and it could also happen that you have stray odor coming from outside, from some other products to inside the package. Or you can have volatile solvent. For example, you have a label. Now, label is printed, for example. So if it's printed, it has ink, and ink may have solvents as well. So those volatiles from the inks can also come. You have molecules that are present inside the product. They can also come into the package, and they can also transmit through, or they can also be sorbed. So let's first try to understand the product package interaction. Now, why we have product and package interacting? So if you look at the molecular level, your gases, whether it is water, you have carbon dioxide, your oxygen, gases that you have, at the molecular level, they are chemicals. Your package, which is polymer, polyethylene or polypropylene or PET, that is also a chemical. Those are macromolecules, right? And then your food is also made up of various biomolecules. So your package is a chemical, your product is chemical. So when you have two chemicals, they would react at some condition. Now, what that condition is, that will depend upon the particular product and package system. It may or may not happen at ambience or refrigerated condition, but at some condition, it will definitely occur. And that's what we want to avoid in a lot of our packages. When we talk about product package interaction, we can primarily divide it into three categories. You have permeation or transmission happening, right? You have sorption and you have migration. So what is the difference between these three: permeation, sorption, and migration? When we talk about permeation, you have transfer of molecules, gas, or you have moisture, or you have volatile compounds from the product, like flavor compounds from the product. They're going from either inside to out or outside to inside. That's what is permeation. So we talked about the pressure difference will determine whether they are going in or they are moving out. Now, it will also vary on the permeate and the plastic used. So if there is a likability between permeate and plastic, you will see more of the gaseous or moisture moving in or out of the plastic. So what is sorption? Now, sorption is uptake of compounds For example, you have flavor components that are present inside the product that is being taken up by the package. And that loss of flavor is, it will affect the quality of the product, because your consumer may not like the product anymore, or it may be less desirable. So where would these molecules go? They are not leaving the package. They are going to stay inside. Excuse me. They're going to stay inside the amorphous areas of the polymer. So they are part of the plastic. They become the part of the plastic. So something which is going from your food product into the plastic and it stays in the plastic, that is sorption. And so what is migration? Migration is, you have various molecules which are present inside the plastic. And where did they came from inside the plastic? Either they are unreacted monomers or partially reacted partially reacted chains, or you have some kind of additives, you have some kind of colorants, you have catalyst, you have any kind of molecules which are a part of the chemistry of the plastic. They can also come out of the plastic. Plastic can kick those out and they can come into the product. And why would that happen? Because at times plastic crystallizes, it kicks out, or at times the product that you have, it likes some of those additives or some kind of chemicals. It likes and it binds and it pulls it into the product. So I hope these three terms, permeation, sorption, and migration, they are pretty clear to you. These are the kind of interactions that can occur between the product and the package. So you have little more verbiage here to explain this concept of sorption. Now, the compounds that are sorbed, they are also known as sorbates. And the sorption is also known as flavor scalping. Now, we can have migration of various molecules from the material into the product. However, those migrants, what are permissible, particularly when we are talking about food product, they are administered by federal agency. We have a federal agency called Food and Drug Administration, and it determines what are permissible limits of various additives, monomers, or catalysts. And so for every chemical, there is every commonly find chemical, there is a list. What is a allowable concentration in the product that is acceptable? And there are various methodologies to verify and test migration of various additives as well. Let's look at some more terminology. Now, you see the words, you have permeant, adsorption. So what is a permeant? A molecule which can pass through or into a membrane or polymer, that is what we call as permeant. And also, we have talked about sorption. There are different terms. You have adsorption and absorption. So what is the difference between the two? Now, adsorption, add with the D, that is a surface phenomenon. When we are talking about adsorption, that means molecules are binded on the surface of another material. And when we say absorption, it's going into the bulk. It's being absorbed by the bulk. Also, I would like to point out here, you can see in the slide, permeability and barrier. Now, permeability and barrier are opposite terms. Higher the permeability, lower is the barrier performance of a material. Sometimes students get confused between the two. So if you have higher crystallinity, you tend to see higher barrier performance, or you see lower permeability through the material, because you tend to have less space between the chains, and molecules cannot pass through those areas. So I mentioned about crystallinity and distance between the chains, right? So the amorphous areas in the polymer, we talked about amorphous versus crystalline region. We talked about spherulites before, right? So the amorphous areas inside the polymer are the areas where technically we have voids, we have free volume. And those areas are not occupied by the polymers. So that is what facilitates, those voids are what facilitates the movement of the permeates from one side to the other side, and that encourages or increases the permeability of the molecules. Crystalline areas, they do not allow the gas molecules to pass through, particularly so in the polar molecules. So now here I have a schematic. Think like you have a film, right? And now in the real world, we do not just have one gas or one molecule, right? So for example, if I have a product, I have a package, the package would be exposed to all sorts of gases, right? It would be exposed to water, it would be exposed to oxygen, it would be exposed to carbon dioxide. Now, some of those molecules may move in and out of the package, others may or may not move, right? Or it may move at a different rate. So to understand this concept of competitiveness, you have a film here, right? Think like you have a plastic film here. This is the cross section of the plastic film. Now you have gas molecule A, you have gas molecule type B, right? Now the schematic here is showing you the less of type A molecules, which are in red. They are moving from one side of the plastic to the other side. You have more movement of the B-type molecules, which are green, from left to the right, right? So, all molecules may not be moving at the same rate. What determines the permeability? The interaction between this permeant red and green, it will determine whether how fast it will move through. So if this red molecule likes, it will adhere to the surface, what we call as adsorption. And then after it is adsorbed, it will be fused through the polymer chain and it will go to the other side. But if it's not liking this plastic, then it will not move as quickly. For example, consider you have a polar plastic here like EVOH and PVOH. EVOH or PVOH, polyvinyl alcohol or ethylene vinyl alcohol, they are water sensitive, right? So that means they like water. So if my plastic is like, for example, EVOH and PVOH, and let's say my green molecules, they are like water is going to quickly bind onto the surface of the film, and then it can transmit through quickly. On the other hand, let's say it's some other molecule which does not like that particular plastic, then it may not permeate through. So the rate of adsorption, that is before the molecules transmit through, the rate of the adsorption is very important for the permeability to happen. So to understand a little more of the rate of adsorption, there are other factors which can make a difference. The rate of adsorption, let's assume I have this ball right here, or a molecule, and I have this surface in the blue, and then I have some molecules like yellow right here. Now, consider you are in a closed atmosphere, right? If you are in a closed atmosphere, here I have four molecules which are interacting with the surface, right? Think like instead of 4, I have 10 of these molecules, and it's a closed area, right? If I have 10 of these molecules, that means I have more of these molecules, which indicates there is more pressure. So if there is more pressure, then more of these can interact with the surface. That means the probability of sticking of these molecules to the surface would be high. So the higher the pressure, higher is the interaction. So your rate of adsorption is impacted by the kind of interactions that are happening between the surface and the gas and the pressure of the gas over the surface. So how does permeability mechanism occur? So consider this cross section of the film, and you have diamonds here. Now you have these diamonds. Consider those diamonds as crystalline areas and rest of the polymer as amorphous areas. Now you have, consider on the left hand side, the pressure of gas is higher. On the right hand side, the pressure of the gas is lower. Consider in this case you have carbon dioxide. So the movement of molecules will occur from left to the right, from higher to the lower. Now for the molecules to permeate, the first thing that will occur is your carbon dioxide will bounce. It will strike the surface. Some of these molecules, they will bind with the surface, they will be sorbed, and then they will diffuse through the plastic film. So there is no well-defined path through which the molecules can go from the higher pressure side to the lower pressure side. They will try to make their way through. Now it could be the shortest path possible, or it may be a kind of zigzag intertwined kind of pathway, but it will avoid the crystalline areas to pass through. So you have sorption followed by diffusion, and then you have desorption of the molecules. So these molecules are let go by polymer on the other side. Why would a polymer which likes a gas molecule which is adsorbed on one side, it lets it go on the other side? So pressure is the determinant factor here. It is the driving force which is moving the molecules from the left to the right. So let's look at a YouTube video which I created, and here it talks about some of the terminologies like transmission rate as well. Transmission rate of various gaseous molecules such as oxygen or water vapors into or outside a package is an important characteristic of a polymeric material. If we can control the transmission rate of a polymer, we can possibly control the shelf life of a product. All polymers transmit gases or water molecules. Transmission of permeant molecules always occur from high permeant pressure side to low permeant pressure side of the package. In other words, molecules can permeate into or out of a package. Transmission rate of a polymer can be defined as number of molecules transmitting through a polymer per unit area per unit time. The transmission rate numbers can change with varying thicknesses of the polymeric film and the change in the pressure difference between the permeant side and the carrier side. To normalize for the thickness and to account the pressure differential between the two sides, the permeability coefficient is calculated. Transmission process can be divided into 3 steps: adsorption, diffusion, and desorption. The quantity of permeant molecules adsorbed on a film depends on the partial pressure of the permeant and the chemical interactions between the permeant and the plastic film. If there is a high interaction between the plastic and the permeant, then we expect higher permeability of that permeant. On the high permeant pressure side, the permeant molecules adsorb on the surface of the plastic film. Then the permeant molecules diffuse through the plastic film and finally desorbing on the low permeant pressure side. Okay, so I hope the animation was helpful. So particularly the video talked a little bit about the permeability mechanism. In addition, it talked about the transmission rate and permeability coefficient, right? So what is this term transmission rate? As the video mentioned, how much of molecules they are passing through per unit area per unit time, right? So the transmission rate, if we are talking about gas, we generally in the industry call it as GTR. Sometimes we utilize the terms OTR for oxygen transmission rate. For carbon dioxide, we use CO2 TR. When we have water vapors, we call them WVTR. So so that's the common terminology. How much is flowing through per unit area per unit time? Now, remember we talked about pressure. Pressure determines how fast the molecules will go from one side to the other, the pressure difference between inside and the outside of the package. So did we take that into account? We did not, right? What about the thickness? If I say I have 1 mil thick film, I say I have 3 mil thick film or a package, right? And I have what do I expect? Naturally, the thicker film will allow less molecules to pass through, right? So how do we take into account those things? We mathematically take into account those things, and that is what is permeability coefficient. So permeability coefficient is a fundamental property. It's a mass transfer property of a particular membrane or a polymeric matrix. And gas transmission is like a flux. So irrespective of if you are using 1 mil or 3 mil thick film, if they are same material, they are processed exactly same way, then their permeability coefficient would be the same, but their GTR, OTR, WETR, those could be different. And here you have a permeability coefficient, right? Now, permeability coefficient, here you see how many number of molecules that are moving through times thickness divided by area A, time T, and pressure delta P. So this term Q by AT, that is your transmission rate. How many molecules flowing through certain area in certain time. We multiplied it with thickness and divided by the pressure difference, which is delta P, pressure difference between inside and the outside. So we took into account the thickness and pressure difference, and we got the property of the material. So in other words, permeability coefficient is equal to transmission rate times thickness by delta P, which is right here. Permeability coefficient is equal to Q by AT times thickness by pressure difference. So Q by AT is WETR or OTR or GTR times L by delta P. So I hope so far what I have covered makes sense. And I would continue the rest of the slides in the next class meeting. The slide deck is posted. You can look at the slides at your convenience. And if you have any questions, you can ask me in the next class meeting. So I'll stop right here and we'll catch up in the next class meeting. Thank you. Bye-bye.